Welcome back. In this lecture, we will begin to look at more details of a corrosion cell. What is interesting about this is there are two electrodes, but both the electrodes are on the same interface. We will clarify the statement as we progress. So here, a typical corrosion cell is schematically shown. And the reason why we say electrochemistry is hidden in corrosion, in a typical corrosion cell, is that the anode and cathode are not physically separated via an electrolyte. That is the typical electrochemical cell, but in a corrosion cell, that does not happen. So what we see here is that there is a metal which is getting corroded. So the metal can typically transport electrons, and you have an electrolyte. Electrolyte is a typical ion transporter. So at the anodic sites in a metal that is getting corroded, metal is getting oxidized. This is what corrosion means, releasing electrons. And on the same electrolyte, on the same metal electrolyte interface, there are cathodic regions wherein this reaction is occurring. That is, the electrons that are perhaps released from this reaction is combining with protons to form water and hydrogen. So what is to be noticed is that the anodic region and the cathodic region are in the same interface. So this imposes certain constraints. What is the primary constraint? So in many electrochemical systems, the electrochemical system might involve supply from an external source. But as opposed to this, the electrons that are generated from this reaction has to be consumed by this reaction. That is, when you have an oxidation reaction that generates electrons, and at steady state, these electrons have to be consumed by a reduction reaction. So if that is not the case, the electrons might accumulate in this metal. The potential of this metal will change, and in turn, this reaction might get suppressed. So at steady state, there is no accumulation of electrons in the metal. So all the electrons that are generated here is consumed in a reduction reaction at the same metal electrolyte interface. So this kind of situation is often referred to as generalized corrosion cell or a uniform corrosion cell. So at this metal electrolyte interface, the potential can be established using this equation. That is, the anodic site's potential is determined by the concentration of this species. An increase in the concentration of this species will subsequently increase the potential at this interface, and a significant increase in this concentration would suppress the capacity of this site to act as an anode. So even without considering certain changes in the metal, changes in the electrolyte because of change in the concentration of this species would determine the capacity of that site to act as an anode. Likewise, the environment in the vicinity of the metal in the electrolyte also changes the electrode electrolyte interface potential. So the potential in this case is affected by the concentration of proton and the concentration of hydrogen. So by varying this, this potential gets modified, which in turn modifies the capacity of a particular site to act as a cathode. So what is to be understood is that in uniform or generalized corrosion cell, anodes and cathodic sites can fluctuate. What was once, let's say, an anode can become a cathode because of changes in some relevant species, and what was a cathode can become an anode. So this is the case in the case of uniform corrosion, but as opposed to uniform corrosion, in the case of localized corrosion, these examples are examples of localized corrosion. Here, there can be distinct sites which will permanently act as anode and cathode. Here, as opposed to these scenarios, what was once a cathode can become an anodic site and the other way around. So let us first look at the reasons why there can be permanent electrodes in the case of localized corrosion. So these interfaces in localized corrosion can be made up of two different kinds of metals. For example, if you have a copper iron interface, this is perhaps a very common interface because both are commodity metals. This kind of interface exists in many applications. So between the two, copper is more noble compared to iron. So one of the metal will typically support a cathodic reaction. The other metal, which supports the anodic reaction, will tend to get corroded. For example, if you have iron and copper, iron will get predominantly corroded because it is less noble compared to copper. This is the case in galvanic corrosion. We will look at this example in some detail in a later lecture. So there can also be inhomogeneities within the same metal. Okay, so this inhomogeneity can be physical or chemical. What do you mean by that? Is that the microstructure of some parts of the metal can be different. For example, it may have cracks or it may have certain facets which are predominantly exposed. So even when the chemical composition is the same, the microstructure might introduce significant inhomogeneities, making a particular metal more anodic compared to certain parts of the metal. So there can be structural inhomogeneities. These are all classified under physical inhomogeneities. In other cases, there can be chemical inhomogeneities. For example, if you have an alloy, the composition of the alloy can be different in different places. Because of these compositional inhomogeneities, there can be gradationness in gradation in nobleness. So the areas which are less noble might act as a permanent anodic site, and the areas which are more noble will act as a permanent cathodic site. So what I'm trying to convey is that as opposed to uniform corrosion, generalized corrosion, in localized corrosion, physical and chemical inhomogeneities might lead to gradation and nobleness. There can also be gradation in electric field in the same material. For example, when you have structures under, let's say, in the vicinity of high voltage electric lines, there can be stray electric field um, imposed on structures. Because of this, some regions will act as an anode and some regions will act as cathode. So this creates permanent electrodes in because of electric field inhomogeneities. There can also be autocatalytic mechanism which create permanent electrodes. So let's look at one such mechanism. For example, if you have iron may get oxidized to Fe2 plus. This is typically a slow step. However, iron, that is Fe2 plus formed from this reaction, might react with oxygen present in the aqueous environment. Oxygen is typically, there will be dissolved oxygen in water. Fe2 plus will react with oxygen and protons to form this species. This species is very reactive with respect to zero valent iron. Okay, this is iron that is present in the form of a solid. Fe3 plus will react with Fe in the zero valent state to generate divalent Fe. So this is a fast step. So the overall reaction, putting all these things together, can be iron reacting with oxygen and protons to give you trivalent ion, which in turn will react with oxygen and form Fe2O3, which is your common rust. So when you say iron is rusted, you end up with this compound. So this is an autocatalytic mechanism. So if some parts of iron are exposed to oxygen of higher concentration, so that those parts will tend to form in those parts this reaction would be more possible as opposed to regions which are exposed to less amount of oxygen in its vicinity. So these are some of the mechanisms which lead to permanent electrodes in localized corrosion. So in the next lecture, we will look at elementary aspect of thermodynamics, which will give a criteria why certain materials do get corroded. We will look at this topic in the next lecture. Thank you.